This is our third session, but only our second presentation. So don't be concerned that you missed something along the way. Last week we covered two aspects, and this week we are looking at chemical deformation of concrete. Now, chemical deformation, you would say, what would chemically deform concrete? And chemically deform, the general rule is anything that with water can get into your concrete is able to deform your concrete and have a negative impact on the structure of your concrete or your matrix or the glue that gels everything together. So last week we covered the glue and we covered some of the physical deformations, things that we generally understand and work around every day. Chemical deformation is slightly different. In terms of deformation and physical deformation, the closest one that comes close in last week's presentation would be the carbonation shrinkage or the shrinkage aspects of concrete, even though that happens during its fresh state and also during its mature state. Chemical deformation, as we'd like to explain it, covers these four topics in very basic terms. Your alkali-silica reaction, heat of hydration, sulfate attacks, and chloride attacks. We'll breeze into alkali-silica reaction. It is also known as aggregate silica reaction, and it's a reaction between the reactive silicas or reactive silica constituents in the aggregates and then the alkalis in your cement paste, and it needs water to happen. If there's no water, nothing will happen. It's very interesting that this, in a sense, happens in the gel or happens in the cement glue matrix, but it needs the aggregate to be able to perform its destructive tendency. So it's literally a reaction on the surface of the aggregate where it is in contact with your hydration products, your CSH paste and your CH paste, calcium hydroxide and your calcium silica hydrates. The reactive forms of silica typically are noted here: opal, which is amorphous, chalcedony, which is cryptocrystalline, and tridymite, which is also crystalline. Now, these are reactive components in aggregate, and we have these reactive aggregates in South Africa and all over the world. The reactive minerals are also noted here. So if you maybe heard that you have rhyolitic aggregate or andesite or phyllites, these are the ones that we are aware of and that we work with in South Africa. As soon as you cross the border, you're going to different aspects, but if you understand the process here, the mitigating matters are very much the same. So to recap on the process, is that we need a reactive silica that reacts with alkaline cement. It forms a silica gel at the aggregate interface. In connection with moisture, it gives you a bunch of swelling, and the results are tensile stresses and crackling. So you can just imagine you have this set matrix of concrete that could be months old or years old. And depending on the speed of your ASR, which we also like to call your concrete cancer, this cancer happens inside your concrete. It literally starts at day one, if you could say that, but it might not be as noticeable in the early stages, and it becomes more pronounced later during the age of your structure. So I'd like to highlight the three components or the three legs for this chair. Without any one of these three legs, the chair won't stand and you will not have ASR. So if you can completely avoid silicas, or you could completely avoid alkalis, or completely avoid moisture, you're okay, Jack. But these aspects do sometimes pose a bit of a challenge in isolation. There was a lady that called into East Coast Radio a few years ago, and she was complaining to the TJ at the time about the government. So I don't know if anyone's complained about the government before, I cannot believe why you would. But she was complaining about the government. And specifically, she noticed that they were painting bridges on the N2. And she went off on a tangent about the amount of potholes that are in the suburbs and on the roads, not on the national route, but on the local routes and that. And there was a long chat about this, and people calling in and complaining and saying, yeah, they agree and all that. Now, what happened in the background is that eThekwini municipality noticed that, listen, by mistake, we've used reactive silica aggregates in many of our bridges over the years, which inevitably points towards ASR. It is given. It might be 40 years for it to happen, 30 or 20, but we are sitting with a problem where we are using quarries all over the show, and we are looking at the best price in terms of aggregate. So some of these quarries have reactive silica aggregates, and they were used in these bridges. And the only way that the client could then say, okay, let's try and mitigate the damage, was to say, let's try and avoid moisture. So they were painting the bridges, they were sealing it with a surface applied water sealant or a waterproofing agent. Now, whether this was a cementitious, I'm assuming it would have been a cementitious. I don't think it would be an epoxy base, but it could be either of those. They were trying to limit any further ingress of water. Now, if you remember from last week, we said that your concrete uses about 40 liters to 60 liters of your water that you've given it into your mix to create gel crystals, your CSH gel crystal, and also some calcium hydroxide. It's not using all the water. So eventually, you might say that the term of concrete drying out might apply. Your concrete will lose its moisture over time. But some of the moisture in there stays there for a very long time. If you can imagine a massive piece of concrete, a bridge base, if it's underground, you cannot remove water in there. You cannot. The water will be there. There's no way of sealing it. But generally, stuff that's in the ground don't fall on people that's driving below it. It's the stuff that's suspended in the air that falls down on people. So if you want to prevent the first floor becoming the ground floor, this is now what they were doing. They were sealing those bridges to prevent further moisture ingress, which would then fuel this whole ASR process. So the reaction starts by attacks on siliceous minerals available in the aggregate. And this is, the reaction is with the alkaline hydroxides from the cement paste. As a result, there's a whitish gel formed on the surface of the aggregate. So it completely envelops the aggregate. So this is a process that doesn't happen inside the aggregate. It happens on the surface of the aggregate and in the pores on the aggregate as well. What it then does, it destroys the ITZ zone, the interfacial transition zone. This is where your cement particle was sitting in space with a solution of water, and it's now reacting, and it was growing gel particles, and it's touching your aggregate. It's not gluing itself to the aggregate, it's literally touching. And if you surround this aggregate particle, you end up with a situation where this aggregate particle now becomes locked in space, as does the one next to it, and the little sand particle, and a coarser sand particle, even a finer particle, and cement particles, and GGBS particles. Just imagine all your particles inside your concrete matrix. It's not just 19mm stone, it's also sand, and it might be manufactured sand, and there's a component of dust, and then there are cement particles, fly ash particles, anything that was put inside the concrete. It has a little bit of a shape, even though it's a micron in diameter, or whether it's a 20mm diameter, it becomes part of this. So it destroys that matrix zone immediately around your siliceous aggregates. And if you start losing that zone, you start losing bond. So you destroy the bond between aggregate and the surrounding hydrated paste. The gel is unfortunately of a swelling nature, it consumes water and it increases in volume. Now, because this jelly is confined in this surrounding paste that's completely surrounded these aggregates, pressure builds up, and these pressures at some point overpower the tensile forces that your concrete has. Now, the rule of thumb is that a 30 MPa concrete would typically have a 3 MPa tensile force. The rule of thumb is about 10% of your compressive capacity would be your tensile capacity. Now, it doesn't take long for it to overpower this tensile force. Yes, factors like reinforcing around your inside your concrete matrix does play a role in mitigating and delaying the actual effects of these pressures building up. But inevitably, it will start expanding and start cracking, and you'll start to observe cracks on the concrete surface. Now, as soon as the cracks are there, water gets in even more readily available. So every time it rains or every time there's precipitation in some form, shape, way, even if it's in an area with high humidity, you have moisture getting into your concrete, getting in here where this gel wants to grow. And that is not a good thing. That is absolutely horrible. And you will find some end products looking like this white substance leaching off the surface and cracking galore. It's cracking everywhere. This thing is cracking. It's not cracks that were put in the concrete when they mixed it. This is a crack that happens afterwards. It's a random crack pattern, so that doesn't help you much. It doesn't crack in shapes that you would recognize and say, okay, so I recognize this crack pattern because it's a random. That's the only recognition that you might have. There's a white rim around the aggregate. So if the guys do exploratory testing for laboratory exercises, they'll probably do core drilling and remove the core, and then they will closely look at your core surface, and you'll find this white rim around your concrete, and this is your ASR that happens on the aggregate surface. So it may take many years to develop. The structural effects are loss of strength, loss of stiffness, cracking, and deflections. So this is no good. This is where you end up, unfortunately, up that creek without a paddle, if I can put it blandly. And to mitigate once you are here, there's nothing much you can do. This is a rebuild consideration, putting it straight. So one of the examples I'd like to share, a few years ago, Lafarge embarked on a project, and they supplied low alkali cement to Maputo, and they were to build a structure in the harbor, and they had to look at, firstly, they identified ASR as a possible risk. They tried to look for suitable aggregates, and suitable aggregates they could find, but the aggregates were too far away from the smelter. Eventually, reducing the alkalis became the only option. Now, there are a few cements manufactured in South Africa that is equivalent of a low sodium or a low alkali cement, as per the ASTM definition. So if there's less than 0.6, well below, then you have a low alkali cement. Now you can go and shop around to even the lowest one, and it was cheaper to export cement to this structure than it was to replace the aggregates. Water they could not replace or eliminate the water. The water was a given. This is in the harbor. There's no way you'll get away from the water. They also added fly ash to the concrete, and this fly ash also reacted with the hydroxides, reducing the alkalis available for the ASR reaction to happen. So this cement came from Lafarge in Lichtenburg, and it was used with fly ash, with high potential ASR aggregates, rhyolites, the Mosel smelter, and bauxite silos in this pier in Maputo. So this is just an example of looking at your three legs of the chair and then picking the one that's easiest to remove. If you have time and if you have the luxury of having that gap before the project actually starts, this is the right plan. The old adage, failing to plan is planning to fail. If you embark on a concrete project, be sure to at least apply the significant number of tests, apply some effort in your research when you start planning for your project. Look at what is available. It's not as simple as saying, okay, so for this structure we need 40 MPa concrete, and calling the supplier and asking him if he can supply a 40 MPa. He's going to say yes. If it's a big enough project, they'll say yes to anything. But you don't know yet at that point what's in your concrete. You need to establish what sort of aggregates you are using, what sort of cement you are using, and what the risks are. This is in the hands of us as the consultants. We have the hands of destiny when it comes to projects like these, which could end up in a failure or to a structure that will at least last its 50 years. It might outlive its purpose during its lifespan. And that's what we want. We want a sustainable structure. So fit for purpose, plan, and make sure that we got the right mitigating matters in place. So heat of hydration. I'm not sure if anybody has experienced this. There are two components of this, and this is quite important, is that you have initial heat of hydration, and then you have the real heat of hydration. Initial heat of hydration happens as soon as water hits your concrete in the back of the drum or in the back of the mixer or in the mixer or whichever process you are using. There is a slight elevation in temperature as you start mixing your concrete, and this is attributed to your C3A reacting with the water, and then also with your calcium sulfide, your gypsum. So as soon as that process happens, there's a bunch of heat that gets exuded from your mixture, and it can bump up the temperature of your concrete between 5 and 10 degrees even in extreme cases. And we've had situations where our clients would deliver concrete, and for a large project, they were lucky enough to secure a piece of property right next to the project, and literally the truck needs to drive halfway around the project site to the gate to gain entry to the site. So they drive about 1.5 kilometers. So to put this into a sort of a timing perspective, is that your concrete truck is batched in about 10 or 11 minutes, depending on your batch plant processes and optimizations. That's typically how long it takes to get that truck filled up completely. Some of these plants are quicker. So if it's about 10 minutes, you know that your concrete plant has the capacity to batch about 60 cubic meters of concrete in an hour. So you have, or even less, let's use 6 minutes as an example. But let's park that idea. What happens then to the concrete truck? As soon as it's batched, it removes itself from under the plant and it goes and parks at the inspection platform, where the concrete is then monitored visually for slump, whether the mix is responding according to the mix criteria and the mix design that was prescribed. So there's a batching process or a batching sequence that's followed. Your coarse aggregate, your fine aggregates, your cement and your cementitious extenders, as well as your admixtures, all get added or pre-batched, then loaded into your truck and mixed. And there's a bit of a regime of loading it. You can't chuck all the dry stuff into your concrete truck at first. You need to put a bit of water first, and then a bit of coarse, and then follow with fine. And it's all the process of batching, but generally it happens quite quickly. So let's say 6 to 10 minutes, and you sit with this truck at your inspection platform. It remains there for about a minute or two. After which, if everybody's happy with the slump in the back of the truck then departs for the site. And in this specific case, the truck didn't have far to drive, 1.5 kilometers. within 5 minutes, he is entering the site. And then for shrinkage constraints, the consultants and the client specifically made note of the concrete placement temperature. If the concrete placement temperature is above 30 degrees, the concrete gets rejected. So now this truck then pitches up on site, and even this, as the temperature was taken at the batch plant, let's say 25 degrees, after about 5 minutes, it's on site, and the slump is taken, and somebody pokes a thermometer into the little wheelbarrow that was placed there for testing, and says, "Oh no, 31 degrees, 32 degrees, concrete rejected." Take the 6 cubic meters and go stuff it where the sun doesn't shine. Now the truck has to come back to the plant. And then what did they do with 6 cubic meters of concrete? I mean, that's 6 cubic meters of concrete. That is almost a ton of cement. That is a lot of material and a lot of effort that went into that. And they couldn't come around the process. So one of the guys on site attended the course here, and he said to me, "Rian, but I think this is initial heat of hydration." And I had that on my lips as he was explaining the situation. I said, "Okay, so what you do, keep the truck on your site for 30 minutes and then monitor the temperature. Find yourself one of these COVID infrared thermometers. If you want to buy a little bit more expensive one, a major tech one, and it gives you a little LED so you know exactly where you are measuring. And then stick that into the back of your truck and monitor the temperature. Every 10 minutes, get a feel of what's happening. You're not going to measure each and every truck for the duration of the project. You'll start seeing a tendency. You'll start seeing a repetition of a process. Listen, okay, so we start batching, it's 23 sometimes, it's 25 sometimes, and then the temperature starts rising, and then the heat dissipates. So what happens when the heat dissipates? This is where your C3A and your gypsum has already reacted. It's formed ettringite, and now this ettringite is covering everything. The inside of the drum, it's covering the aggregate, it's covering that rubber glove that by mistake went into the concrete also. It's covering everything. And this ettringite, now this process stops, and the ettringite is there for 1.5 to maybe 3 hours, delaying the actual hydration of your concrete. So no more heat gets built up. Your drum can now slowly run, and the heat gets dissipated to the atmosphere. And sure as Bob, these trucks started cooling down. They went up to about 32, 33 degrees. And then after a few minutes, you see the temperatures lowering. So as soon as it went below 30, the trucks were dispatched to site. And when they got to site, easily achieved 25 degrees centigrade, which then conforms to the temperatures requirement of the consultant and the client. Yes, if you were to place that concrete while it's in its initial heat of hydration, you are now breaking the rules, because you are placing concrete that is warmer than 32 degrees. You are putting it into a shutter, into an opening, into an excavation, and that heat then gets trapped. It's like a cool bag. That 32 degrees will stay there. It might be maybe 31 on the surface, or maybe a little bit cooler on the surface, but in the core it remains 32. Because it's not being mixed, it's exposing less surface area, and it cannot exude that heat fast enough. So you're breaking the rules that was put down by the consultants of placing at that temperature. So let it mix. It doesn't do the concrete any damage. It actually benefits your performance of your concrete while this process is ongoing. Your ettringite will not dissolve quicker. You are quite safe in terms of that. But then monitoring that is very important. So we had great success with that. And when the concrete supplier was completely with his hands in his hair, he had a solution to look at. So initial heat of hydration posed a little bit of a hurdle for him. Now, there's a very broad statement made here that hydration of cement is an exothermic process. Energy is up to 500 joules per gram. Now, if you can remember back to grade 9 or to standard 7, depending on your age, I'm giving my age away, you would remember that one joule of energy is enough to heat 1 gram of water by 1 degree centigrade. So if you're putting 500 joules in there, that's a lot of joules. That's okay. It's a half a kilojoule. So it's not much, but That's per gram of cement. It's every gram of cement. And the reason it's doing this is we put this calcium carbonate and extenders and correctors into the kiln, and we burned it for almost 30 to 40 minutes in a kiln at 1,450 odd plus degrees centigrade. It's now getting back at us. This is it getting back at us. It exudes this heat. It's taking back that energy and it's exuding it. And that temperature builds up in your concrete. We know that concrete has very low thermal conductivity, so it actually acts as an insulator. Some time to heat up, but it can hold that heat. In mass concrete, the heat created by hydration could lead to a significant rise in internal temperatures compared to normal structures. So back in the day, we used to mix, and I cannot remember the strength of concrete that we used, but for the sake of simplicity, we used fine aggregates, and this was at technical stages. And we made a little block, 300 by 300 in a wooden shutter. And I think it was a 50 or a 60 MPa concrete, which we then mixed with river sand, more a mortar really. And the point was to get a lot of cement into that mix. Which cement we used, I cannot recall. At that stage, you were aiming to pass, not really making notes of exactly the cement. And fill this little box halfway, and then we took a raw egg in its shell. We inserted that into the center of this plus minus center of this little cube, and then we filled up the rest of it. And then 3 days later, we came and we cracked the cube. We cracked it open, and we removed from this cube this egg, and it was hard boiled. So that's a very cumbersome and high effort way, but you could cook your eggs like this. If you prefer hard-boiled egg for breakfast, this is a fantastic way of doing it. It does take 2 days though. But that is just giving you an idea how much heat is inside that concrete. So the rule of thumb with heat of hydration is that there should not be a temperature gradient between the core of your concrete and the exterior surface of more than 20 degrees. If you have that temperature gradient of more than 20 degrees, you can imagine that your center is warmer by 20 degrees more than the outside of your concrete. And if something heats up, it tends to expand. Now, if it's expanding and the outside is not expanding, you end up with cracks on the surface. So this looks almost like a 3D crack. If you've seen pictures of bulletproof glass hit with a bullet, and you see that center, and then there's a bunch of circular cracks around that, and there's a bunch of lines running from the center, and even more, almost like a stone in a pond kind of ripple effect that it runs out as. Imagine that in a 3D, not in a 2D plane. That is typically how your cracking would happen. So it's unfortunately also random. So you might not be able to establish between ASR and heat of hydration if you look at these cracks, especially if there's no white substance leaching from the one. So it might even look like an ASR type of crack. It's everywhere. And it's quite disconcerting. The cracks will open up, and eventually the cracks will close up again, but they will still be visible. And because it's cracked, that opening is still there. So you will still have the possibility of moisture ingress inside your concrete that can bring in stuff, the baddies, into your concrete. We'll chat about the baddies later. That is part of the chemical thing. So it's very advisable that you know the heat generating properties of your cement that you are using in your specific concrete. We had a case where we were casting a 25 MPa concrete base, and just a side note, it doesn't really matter whether you are casting a 40 MPa and it's going to be so hot. No, it could be a 25 MPa. And if the concrete dimensions are massive enough, you could sit with a very real situation as a problem presenting itself as heat of hydration. So it's not just, it's a high-end performance concrete, we might have risk here. You could have heat of hydration considerations in a 20 MPa concrete. I'll tell you a story about that one as well. For practicality, it is not necessarily only the total heat of hydration that matters, but also the rate of heat development and the peak temperature achieved that needs to be considered. So if you can generate the heat over a longer period, more of a flatter graph, you would have a lower peak, and you will benefit from the dissipation process of the concrete. Your concrete matrix will then dissipate the heat, and the heat dissipation is typically at a standard kind of rate, but you might not have control over that. You do have control over the heat generated if you specify your binder, your cement. If you go and you say, listen, I need a cement that's slightly coarser. So I'm putting that as a little seed there. The finer your cement, in other words, your 52.5s, 42.5s, will have a higher initial and ultimate spike of heat of hydration than would have your coarser cements at 32.5 or even at 22.5. Those aspects are completely different. Now, there was a project where heat of hydration was a major concern for a dam wall in the Lesotho Highlands, and a Chinese company, Sinohydro, was tasked with the construction of the dam wall, and it was constructed with a roller compacted concrete. Concrete grade strength 20 MPa at 90 days. That's what they wanted at 90 days. They embarked on a rigorous testing regime with the cement supplier, and they eventually sat with the maximum fly ash extension on this concrete, but they were still gaining too much of strength over 90 days. They were sitting at about 28 MPa. So they really wanted to bring that down. So they further extended. The ultimate extension was 65% of fly ash into this concrete, replacing 65% of clinker. That's the ultimate extension that they settled on, and they took a bunch of cubes. So they were constructing this dam for a year or two. And the cubes taken, by the way, they were scalped cubes. Scalped cubes means that the aggregate particles in some of these, well, in this mix, I think the maximum aggregate particle was 65 millimeters. That's as large as your fist. And then they graded the aggregates down, and the larger aggregate also contributed to a lower paste value or a lower paste component. And there's less surface area to cover with paste. So you also have less risk of hydration and of shrinkage, and the list goes on. So they took it to the ultimate. And in order for you to test this cube, you cannot take a little 150 by 150 cubes and how many fists will you get into that little cube mold? You probably get 3 in there, and then you are stuck. The rule of thumb is you need 4 times the maximum aggregate diameter should be your cube mold. So that's why we use 100 millimeter cube molds for anything using a 20 millimeter. You could go to a 26 millimeter aggregate, but you would be breaking the rules. It's better to then go for 150 millimeter concrete test cube if you are using 26 mil aggregates or larger. You could go a little bit larger up to your 36 millimeters, and then you have to use a larger cube, or you would need to scalp the cubes, removing the larger particles. Now, why would a large concrete test cube be a problem? Your MPa is a force over area. If you have a big block, you need to put one hell of a force on that. If you have a small block, you can apply less force, do the calibration and the calculation. You can calculate, okay, so if I apply X kilonewtons to the hydraulic ram over here, over my 100 by 100 test cube, I've got 30 MPa, 32 MPa, whatever I've got. And if it cracks, you can easily record it. And it's a much smaller size machine. That's a cheaper machine to have. You don't really have the luxury of a 200 or 100 ton press at a construction site way in the boonies back in Lesotho. That's not practical. But anyway, needless to say, the test cubes taken were tested for a period of about 5 years afterwards, and the strength continued to grow. The temperatures inside the concrete never exceeded 25 degrees centigrade. So that temperature probes in the dam, each and every, let's say, 4 or 5 layers of roller compacted concrete, they installed a temperature probe to the closest possible center of the dam, and also on the perimeter to monitor these temperatures as they climbed and subsided again afterwards. and 25 degrees was never exceeded. Now, 25 degrees sounds very low, but if you know Lesotho, that place can become quite cold. So 25 degrees was the conservative value, and that had to be maintained, not to completely lose track of the 20-degree gradient difference between the core and the surface. Let me jump to the next slide. The most important note here is the fineness of the cement has an impact on the rate of heat development. As an increased surface area will speed up the reaction. The finer your cement, the more surface area. You remember we said a 52.5 has about 650 square meters of surface area over all the cement particles for 1 kilogram of that specific cement. And a 32 would have about 400, 380, 350 square meters. That's about double. And your surface area, that's in contact with moisture that reacts. So it's more area that then reacts in your concrete matrix. So this directly causes early age heat development from hydration of cement or cementitious content. Effects are like those of drying shrinkage, and it has a random crack pattern. So there's a little picture on the side. This is a quick column that unfortunately suffered some heat of hydration cracking. And if you look at it, it looks horrible. It looks like crazy cracks. It's just everywhere. Yeah, we had a case, a gentleman that attended one of our courses. They were doing a base for a mine, a fan base, and I think the base measured something like 4 meters, 2 meters, 5 meters, the 3 dimensions. And he noticed the crack along the middle of this base. So initially, that was the only crack he noticed, and he took pictures. And this was 2 days after the cast. And he then went and asked, listen, did you guys check heat of hydration on this? Heat of what? So that answered his question. They didn't clear it up for them. So he said, listen, you've got a problem. Your base cracked already. You haven't even put the fan on it. This fan is going to provide ventilation underground for many people. So this is a safety concern. If this base were to disintegrate and the fan ends up flying instead of blowing, you're going to kill people. Not just people on the surface, perhaps, but also people underground. And they quickly ran and they found out, okay, placed a 30 MPa concrete, and it was extended by about 11% of life, I think, at the point. But that was not enough. It was just too massive, the concrete, and the temperatures were way too high, and they didn't take any mitigating matters into consideration when they placed this concrete. Inevitably, they rebuilt the base. Just a side note, as he took pictures of this crack at day 2, a week later he was there and he went looking for the crack, and the crack's gone. And then he looked closer and he said, the crack is still here. It is now, it's a bit narrow, so it reduced its width because this whole thing now contracted again. And he was able to show it in the picture and say, this is what you had, this is what you've got now. What can you do? So they were considering sealing up the crack or cracks, the other ones that they could find, but that doesn't help. Your whole base has now been split right through the middle. So that's no point. That crack goes in, who knows how far. You'll have to follow it with a core drill and establish how far the damage is. How do you seal up that whole crack? You need something that is sustainable and that's safe. So this little illustration shows us heat of hydration, and then when the peak of this specific mixture or concoction of cement happened. So you'll notice here the red line. This is an ordinary Portland cement, or let's call it a SEM1 cement, that peaks at 48 hours and it's almost 70 degrees. Now, inside your concrete, you never want to exceed 70 degrees. You could go there, but if you imagine a cup of water that is 70 degrees, you just boil the water for a cup of coffee or a cup of tea, and you wait for it to settle down a bit to 70. That's scalding hot. That is very hot. It steams on the surface, and that's part of the problem. Much of your water then starts steaming inside the concrete as well. So that's another problem. where you could have temperatures so high in the center of your concrete that your cement stops hydrating with your water because it's just vapor. It's no more moisture. It's just vapor. It's a high humidity, but it's not wet. Becomes a problem. Two other comparisons here. This is an OPC extended with 30% fly ash and an OPC extended with 40% of fly ash. And you'll see that the peak temperature moved on to 72 hours, and the temperature is about 60 now, 63 maybe. It looks like there's a 7-degree difference over there. And if you further extend it, you can bring the peak forward to 84 hours and have a temperature difference of 12.6 degrees for this specific application. This is not general for each and every concrete out there. This serves to illustrate using the same binder, but extending with fly ash. You could also extend with GGBS, depending on your application and availability of it. But fly ash generally is very available. Looking at some examples, a typical Powercrete Plus of 42.5R will exude 227 joules per gram at 41 hours, and a Civilcrete, a 32.5, about 166 joules per gram at 41 hours. So the term a low heat cement, LH, with an energy generation of less than 270 joules per gram at 41 hours, as per SAMS, tested according to EN 196-9, the semi-adiabatic heat of hydration. So it's tested, and your cement supplier will be able to give you this information if you are asking the correct questions. It's very much the case of if you don't know what to ask, you don't ask it. It's very obvious, but you need to look at, if you're armed with this, you can now ask questions in your specific project where there are a slight chance of heat of hydration considerations. Now the next graph is quite interesting. So the first site here was a job site for Aberdale that we were involved in, and the job scope included that we need to place 100 MPa concrete, and okay, that was fine. Then they said, okay, but the walls are 600 thick. So, okay, all right. Rule of thumb, as soon as any structure is thicker than about 450 millimeters, you might have a situation where heat of hydration could play a role. If you have a strong enough concrete or a high strength concrete, that could play a role. So you need to check for that. Many of the practitioners out there believe that, nah, if it's thicker than a meter, you need to be considered, or need to be concerned. But no, you could see from the information that we've been able to gather from site that that is not the case. We installed temperature probes in the center of a test panel that we cast on site, in the outer face, on the top of the wall, and then we had an ambient sensor. Now you can see the date here, it was in 2016, and on the 21st of April, we placed the concrete. Well, I apologize, on the 20th of April, we placed the concrete. It might have been on the 20th sometime. The exact date of placement becomes quite interesting if you look at the temperatures. I have a picture at some point where the temperature of the concrete initially was above 30 degrees centigrade. So we then learned to allow the truck's time to also just dissipate the heat. Now you become nervous if you are sending a concrete truck with 100 MPa concrete to site, and you know what the temperature was when you tested it. You checked for slump at the batch office, or at the batch plant, and now you become concerned that this temperature is just going to go up. But you can see that the temperature came down handsomely. It came down to almost around 10. But then you also notice that the ambient temperature follows that. And then the ambient drops. And the lowest drop, it was below 10 degrees, about 7 degrees one morning. And then it rises to almost 30. And then it drops to 10, 11, and it's almost 30 again. And this is the temperature gradients that we measured the ambient. Now, if you look at the complete differential over here, the center of this base went as high as almost 60. The top was 58.5, 58.6, somewhere there. This is what the maximum temperature was. And you can see that it maintained that temperature for quite some time. So if we look 1, 2, 3, this is probably 8-hour segments. So that for 16 hours, it maintained that temperature range. So counting 40 hours, you'll see that this is about where 40 hours ended. And that is after placement. So the peak happened quite early. We had a lot of cement into this mix. The top follows the green line, and then the outer face follows the blue line. So already you can see that on the blue line here, we have 10, 20 degrees difference in temperature. And why this is important is that the outer face was exposed to the elements. They didn't cover it with a wooden shutter. One of our mitigating matters was that we prescribed using a 20mm shutter board on those, either a Perivian or a Formscaf shutter to help and insulate, keep the temperatures inside as constant as possible. If you expose the outside, then you lose the heat. And then we were able to determine from this that you need to wait 1, 2, 3, 4, almost 5 days before you remove those shutters. Those shutters will be a cooler box or a jersey or a jacket that this concrete is wearing for that time period until your temperature differentials settle out and you do not jump above the 20 degrees. Then you are ensured that you will have a good temperature range. Now you'll see that the green line follows it starts following the ambient temperature curves. The red line also at some point it does do that. The very lows during the early mornings and the sort of highs in the afternoons does play a role with the temperatures. But this is the graph that we then used on this trial panel to also further establish that when you place the base, so the base gets placed and the base is also 600 thick, this 100 MPa concrete, we covered it with plastic, and then we put shutterboard on top of the plastic. And the temperature under that board was close to 50 when I went and measured on day 2. Put my thermometer under the plastic, drop the board again, and then wait a few seconds, you got 50 MPa. It was lovely. This is April, it was quite cold. When you got to site, you will find that all the laborers are gone. You will not see anybody when you get to the site. But when you get to the actual base that was cast, everybody was standing on top of this base because it was lekker warm. It was very warm right there, much better than the 10 degrees outside. So that it's very interesting. You pitch up with your overall and you've got a jacket underneath and you start unzipping your protective equipment because you are heating up on this concrete that is exuding this amount of heat. The second example that we had a 30 MPa placed at PICM Randfontein by PIC Randfontein for gold 1. And in the top, you'll see the red line. This is the top surface of the concrete. And we had a probe in the middle, which is the blue one. And we almost hit 40. Let's say we 37-ish as a max. In the bottom, quite interesting, we decided to also put a probe in the bottom. That's on the fill. So while we are there, put another probe, and you can see that the temperature on the bottom of the concrete, literally on your compacted subgrade, also followed the gain in temperature. And then at some point, the temperature of the concrete above started to cool down, and the base also started to cool down. But at some point, the base was warmer than the actual concrete on top of it. I cannot for the life of me remember the thickness of the base. I think the base was 1 meter thick. And we also opted for a further extended concrete. We went for maximum extension, but we stayed with a 30 MPa. Part of the mitigating matters was also to insulate with timber shutterboard, we wanted to keep the heat on the surface of the concrete, on the exterior parts of the concrete, as close to the core temperature as possible, so we insulated it. We did some initial calculations just to determine what the temperature should be, plus minus, whether we are going to exceed the 70, which will definitely be bad for the concrete, but we did not. So the surface of the concrete sort of follows this 25 to almost 35 concrete temperature range, and then you see that ambient temperatures. There was a few temperatures here, and this was in July. Yeah. So you see, we approached the 0 temperatures over here, and then you can see the top drop off, the top temperature dropping off on the top here, as low as 15 versus a 0, but we never exceeded 20-degree gradient. Over here we have a 15 going up to a 30, so another 15-degree gradient. So this then indicated to us, right, now we are able to strip the shutters. We can remove this insulation, and they applied that going forward to all the plinths and abutments that were supporting the mill foundation. They were able to say, okay, so we need to wait these amount of days before we start stripping that foundation. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, almost 2 weeks, because it's winter. If this temperature gradient was running in the 18s to 28s, 18s to 28s, we would have been able to start stripping the shutters at 1, 2, 3, 4, at 5 days already. But this also gives you an indication when you can strip those shutters. And if you don't plan for this, your contractor will complain, because he says, I cast the concrete today, 2 days later I strip all the shutters, because those shutters will have to be moved over to the next pour, to the next cast. And if I'm not doing that, I'm losing production. So we were able to establish this forehand, and the contractor was able to then price accordingly and then stagger his costs. He could bring a smaller team onto site. They will prepare section A or section 1A, and then 2 days later, section 1B, section 1C. Instead of just completely preparing section 1, they were able to stagger. And then as soon as C is done, 2 days after C, they were able to, or D, they were able to move into section 2A, move shutters over there, because our temperature gradients completely removed the risk of heat of hydration cracking. While I wait for a question, this is the trowel panel that we cast on site. So that's a 600 thick. And this is about, I think, a 2.4 meter high wall. So the center of that went as high as almost 60 degrees over here. This is the same wall. This is the vault wall. Why did they do 3 core drills? So the laboratory was tasked to check, listen guys, are we going to achieve the 100 MPa? And they came at 7 days to core drill and then test the actual core for in concrete strength, the actual strength. So now we are checking, did the hydration process desiccate? Did it overtemp? Was the temperatures too high? Maybe it stopped. Did something go wrong in the concrete? And then they start to drill the first core and they hit rebar. Why they hit rebar? They brought a little metal detector, but this concrete has some steel fibers in it. Not much, about 40 kilograms of steel fiber. And they couldn't find the rebar or find a spot without rebar. So they did some exploratory drilling over here. So the first rendition, they hit rebar and they were able to start drawing them out. And they started measuring 200, 200, 200. And then the second one, they aimed to try and miss it. They hit rebar again. And then the third one, they got lucky. That core tested 86 MPa at 7 days. Now, 86, you know, in a week, that's a lot of this red line over here. A lot of heat that you need to get rid of or to manage. So that becomes very interesting. So we were able to establish that this concrete is going to ultimately reach about 103 MPa over time. That's just another little side advert that I bring to you. Yes, sir. Marius.
Rian, it's Morris here. Yeah, Rian, I know you talk about the heat of hydration and that, but in my experience, when it comes to reinforced concrete, it depends on the structure. You don't always take that into consideration because of your reinforcement assist with your strength of your concrete and your and it also helps if you do get a crack that you know your concrete is not going to be how can I put it it's not going to fail because of the reinforcement. Is that like you, you know it's how can I put it? You know a general rule of thumb to follow, or would you consider reinforced concrete for the rehydration as well if you have important structures like in industrial areas and places like that?
Marius, I think that it's completely accurate. The consultants on this project also designed for these temperatures in order to have enough reinforcement in there to try and mitigate possible cracking. So that it was a twofold approach. What my 2 cents is, if you know what you're going to do and if you're planning for it, you could make some minor changes, because if you don't know how much reinforcement you need to add in to mitigate your temperature gradients, how much reinforcement are you putting in there? It needs to be a real amount where you are able to say, okay, so I know I'm going to hit 48, I'm not going to hit 35, I'm going to have a gradient differential of 40 degrees or 30 degrees or maybe just 20. I can design for that. Ultimately, the client pays for that reinforcement that goes in, for the labor that installs the reinforcement. So my 2 cents is this. If you can have a two-pronged approach, you try and plan around the actual constituents will react like, and you try and mitigate preventative measures and things like that. And you can also design for those values. You've done the homework now. The housework has been done. You know what the temperatures are. You've done the trial panel. Now you can go and revisit the design and refine it perhaps, and maybe save a client a bunch of money if that is the case. If it's a small job, then perhaps your efforts in another 2 hours of refining your reinforcement is not worth it. But if it's a massive job, I mean, this panel over here, they cost a total of 980 cubic meters of this concrete. That's a lot of work. And you do one design. It's one design, and you spend a bit of money on that. It's worth it. It's really, really worth it. And then you are assured of a very fantastic product. You're not worried at night for a day or two and 3, worried about which cracks will pop up where, and another client will complain about it. So yeah, that's my opinion. I agree. Yes, you can design for heat of hydration with reinforcement, but I would say that is your ultimate fail-safe. If you've explored all the other options to try and prevent, it is better than prevent it than to try and arrest it. That's my opinion. Okay, so the question here is, what causes the spike in temperatures at the 20th of July? So looking at this little graph over here, there's a spike of temperature. So the temperature probes were then disconnected. And the modules that, so it's you have a look at the lines that actually, it's the green one under the ground. So there was probably a disconnection or something that happened when these temperature probes, because these temperature probes are connected to a piece of wire that then runs to wherever it goes. And these probes are then removed. It's got a little USB dongle attached to it. And then the information is downloaded. So I would assume that these were then chucked in the back of the bakkie or inside the car and driven to the laboratory before they downloaded this information. So that's probably what happened. And they did not draw the graph, cut it off soon enough. So when the spike starts happening, it's safe to say this is when the probes were removed. From there, actual temperature probes that goes into the concrete. So now they are measuring temperatures and no longer measuring the temperature inside the concrete. I hope that helps. Okay, Renier is mentioning efflorescence. And that whitish substance deposits, yes, salts on the surface. And efflorescence is a very common thing that happens. So how you would establish whether it's efflorescence or ASR is if you drill into your concrete and you remove the core drill and you find that your aggregate particles in the core have a white rim around it, even inside the concrete, you know that it's ASR. If there's no white rim, then you merely have efflorescence. Now, the efflorescence wouldn't necessarily have that many cracks, really. So that could also pose quite a option to look at. And yes, we need to investigate. So if there's something to investigate, it's important to make sure that you've eliminated those considerations. You don't want to frighten somebody and say we've got ASR when in fact you only have efflorescence. So I agree with that. Interesting thing about efflorescence, a part of the whitish substance that leaches to the surface, initially it's carbonate, it's calcium hydroxide that leaches to the surface. Now calcium hydroxide is water soluble. As you remember, it's water soluble. And if there's moisture in your concrete, the fly ash then reacts with it to form more CSH. If water moves through a wall or through a slab, it brings this water soluble calcium hydroxide liquid to the surface, where the moisture then evaporates off the surface and it leaves the calcium hydroxide white crystals on the surface. You can remove that with a cloth. You can wipe it off with a cloth. If you don't do it immediately, that white calcium hydroxide will carbonate with CO2 on the surface and form limestone, calcium carbonate, which you will then have to mechanically remove either by a bucket brush or a scraper or any other mechanical, a rubbing block, or even acid if you want to really remove all of it. I wouldn't do the acid thing. Acid gets sucked into your concrete surface and it's not nice. It's not good for your concrete. Renier, I hope that helps to answer your question. Rowan, dam shows the white seeping through. What can be done, or does the service of dam come to an end? Now, there's nothing you can do to, because now with a dam, you know that the inside of the dam is full of water. So the process would be that firstly to establish the level of damage and how far it's gone. To establish whether your structure is still competent, whether it is able to withstand another year, another 5 years, another 10 years, before it becomes inoperable or inserviceable or unsafe. Now it becomes a very difficult question. At what point do you pull the plug and say, okay, so excuse the pun. At what point do we pull the plug on this dam? You know, when do we take it out of service, or is there something that we can do? Depending on the level of degradation, it could be possible to empty the dam and paint it, but that just is so impractical. I don't think that is the answer. I think the answer is more along the lines of take it out of service, maybe build a new wall in front of it or downstream of it, to then replace the wall that's behind, you know. So that becomes a bit of a worry. If you have that in concrete, it's concrete cancer. Your concrete will get buried eventually. That's just what's happening. Sulfate attack. So 2 images of typical sulfate attack. You can see on the pictures over here. Sulfate attack, as I mentioned, is as soon as something can get into your concrete with moisture, it is able to attack your concrete. And we discussed in the previous session that if you are able to densify your concrete matrix, if you can prevent stuff coming in there, if you can densify it, if you can reduce your macropores, there's not much to be done about the micropores. The micropores is a chemical reaction that is ongoing within your concrete, very fast in initial stages, and then later on with whatever was inside your cement or with what you've extended. So if your concrete has a high sorptivity or a very high permeability or what we term an oxygen permeability index, it becomes a problem because it is almost like a sponge. As soon as you wet it, the water gets sucked into the surface, and that water is capillary suction, diffusion, there's a bunch of them. The water goes into your concrete, and whatever is in the water gets transported through these transport mechanisms, we call them. So your capillary pores, cracks, becomes highways for gunk to go and damage your concrete / your reinforcement. So if you want to steer clear of that, it's good to consider a very good concrete surface with the means available to you. So what is sulfate attack? So sulfates are regular constituents in groundwater, industrial wastewater, and sewage water. So sulfates could be termed as these three. Typically, we have calcium sulfate, magnesium sulfate, and ammonium sulfate. And all three of these have very similar, not exactly similar, but very similar properties and very similar processes. So to explain the process of a waterborne sulfate is that sulfates permeate the concrete in solution with water. It's very important. You need moisture to bring the sulfates in there. And it reacts with your portlandite in the cement paste, your calcium hydroxide or your CH in short. It also reacts with your calcium aluminates. Now the calcium aluminates, you remember from the beginning, we have C3S, C2S, C4AF, and C3A. Now C3A is this boykie over here. This is the one that immediately reacts when water is there, but the gypsum also immediately reacts. They form together to form ettringite, and that then delays the whole setting process of your concrete. But you might have a cement that has excess C3A that did not have a chance to fully hydrate. So as soon as your water comes in and it brings a few sulfates with it, it gets into touch with your calcium hydroxide, your CaOH2, or your CH in short, and your calcium aluminates, your C3As, and it starts reacting. Now, why is that bad? So attacks of sodium sulfates. You have calcium hydroxide with sodium sulfate. It will give you gypsum, calcium sulfate. So you see this byproduct that then needs to be pulled out. Obviously, the sodium hydroxide is also there. So your calcium sulfate is gypsum. If you have sulfates in gypsum forms, gypsum has a volume increase in comparison to calcium hydroxide. So now you're taking 1 unit of calcium hydroxide and you end up with 1.2 units of gypsum for your efforts of not having a dense concrete matrix in your structure. A very similar exchange happens to magnesium ammonium sulfate attacks. The next step that happens is an ettringite formation. So once it starts, there's a concurrent bunch of things that starts happening. So your C3A then reacts with your calcium sulfate, forming your trisulfide ettringite. Now, trisulfide ettringite, very interesting. It is 2 to 6 times more expensive in volume. So now you're grabbing this little bit of gypsum and you're putting twice of it inside your concrete. That ends up building up pressures in the surface, in the outside surface of your concrete, depending how deep that went in, how far that penetrated. This is the process that then happens. Ettringite gets formed and it builds up pressure inside your concrete. So these are the principal reactions: a formation of gypsum and a byproduct of the attack. So you'll have sodium, magnesium, or ammonium hydroxide as the byproduct. So it's gypsum with sodium hydroxide, or gypsum and magnesium hydroxide, or gypsum and ammonium hydroxide for those 3 processes. And they're also tabled over here. The conversion of calcium sulfate into ettringite. So this is the conversion that happens. Calcium sulfate, this is your gypsum, that then reacts with further C3A if it's available, and generally it is, and it forms ettringite, and it's very expensive. And these are your reaction properties. So you sit with sodium hydroxide, sit with brucite, you sit with ammonium hydroxide as byproducts. but also gypsum, calcium sulfate. After the calcium hydroxide has been consumed, the sulfate solution will further react with your CSH paste, yielding even more gypsum. That reaction is a bit slower, but it does happen. So you just imagine this whole thing just keeps on happening. And what happens is you end up on the surface of your concrete, losing the surface of your concrete, literally, as you see over here. The aggregate becomes exposed. You end up seeing your reinforcement. It just is concrete. So during sulfate attack, your CSH paste undergoes a decalcification, forming more gypsum, reducing the CS ratio in the CSH paste, in turn reducing mechanical strength. That's what we don't want to hear. The low Lyme CSH converts to near amorphous serpentine crystals, exhibiting no cementing properties, forming additional gypsum. So it just gets worse. Unreacted C3A reacts with the sulfate yielding ettringite. So the deeper it goes into the concrete, the more C3A that is still randomly hanging around now becomes available, and it reacts and forms more ettringite. Ettringite is very expensive, and it leads to spalling of your concrete surface. If it spalls, your aggregate will be, your reinforcement will start being exposed. The degradation of the CSH paste in the presence of magnesium sulfate is faster and more complete than other sulfate attacks. Eventually, a double layer is formed consisting of brucite followed by a layer of gypsum. This is one way of establishing where you have magnesium sulfate attack. Magnesium sulfate attack is characterized by loss of strength and total disintegration of the concrete under attack. The interesting thing, the overall action of ammonia sulfate is a combination of acidic and sulfate corrosion. So as soon as you put acid with concrete, concrete has no answer for acid. A geopolymer has an answer for acid, but concrete has no answer for acid and sulfate corrosion. It's also characterized by a release of gaseous ammonia, so you'll be able to smell the ammonia exude from your concrete. So schematically, the waterborne sulfate enters the surface. It starts forming this little layer where it reacts in the concrete, and it starts breaking it down. So this integrates the concrete matrix, this gray schematic here, where your surface of concrete becomes completely degraded. An interesting thing is that for sulfate attack aggregates, generally dolomitic aggregate is preferred, because the dolomitic aggregate will not form these little islands or icebergs sticking out of the concrete. The dolomitic aggregate will also wear away or be worn away, a little sort of flush to the surface, and it actually prolongs the degradation of your concrete surface. Hence the fact dolomite aggregates are generally prescribed when you are looking at sewage lines or sulfate attack prone areas. If you lose this aggregate over here, immediately you have more surface area of paste available to react, and it can quicker migrate into your concrete. So this forms expansion, cracking, scaling, aggregate debonding from your cement paste. The severity of the sulfate attack is dependent on the exposure, concrete type, permeability, and availability of water. In order to mitigate, the incorporation of fly ash in the cement decreases the amount of available alkalis, thus preventing the formation of ettringite. So if you have fly ash in there, you can assist in mitigating that problem. The pozzolanic reaction of a fly ash with a portlandite, which is your CH, forms more CSH, calcium silicate hydrogel, to fill the pore spaces. That then densifies or further densifies the concrete inside, and it makes your concrete less permeable. A lower water demand, if you use fly ash, you will have less paste. Less paste is less risk for your paste being attacked with sulfates. So typically, if you have a concrete or a cement that has an extension of more than 25% fly ash, it would be beneficial under sulfate conditions. That is a rule of thumb, and it's also been proven. If you have the luxury, you can have CCA concrete for your outfall lines, and that is a better alternative. But in general, if you want to combat sulfate attack at a more it's called a more affordable way, and you have luxury of extra cover, and you can have sacrificial layers and stuff like that. You could consider extending with fly ash 25 to 30%. That would be very beneficial. A further option to consider is if you use a sulfate-resisting cement. So again, it all happens, it depends on what you're putting inside the concrete. Now, sulfate-resistant cement is in the specification, the EN 197, and there are 3 types that we've adopted. Cement with low or no C3A. So if there's no C3A, there'll be no reaction with gypsum and no ettringite forming inside your concrete. Your type of cement, if you use a C3, CEM3B or C, this is a blast furnace cement. So it means that in excess of 65 or 90% of your clinker has been replaced by GGBS, ground granulated blast furnace slag. You end up with a sulfate-resistant cement. Any cement of a type CEM4, A or B pozzolanic cement, incorporating either silicious fly ash or volcanic ash, will also be deemed as XR cement. So that's another mitigating factor that could play to your advantage. So in terms of water absorption becomes one of the concerns of sulfate attack, amongst others. As soon as your concrete is porous and it can allow water to come into the pathways, you end up pulling sulfates in there if you have sulfates in the water. So note over here that there was a 28-day and a 56-day string, and you'll find that on a pure CEM1, just at a later stage, your water absorption value drops. If you use 10% of silica fume, it drops even further. And there's a further drop if you take the string to 56 days. And if you use a superpods, which is that's fly ash that is just been more finely classified at the factory, you have even a better performance. So if you keep this as low as possible, you also aid in preventing sulfate attack from being as fast as it could be if you have a very permeable concrete or a weak concrete matrix. The next item we discuss will be chloride attack. Now, we all know chlorides at the sea or at the coast, we'll definitely have chlorides in water. Chlorides can also be present on raw materials for concrete production. So it could also be in your dune sand. If you're using dune sand for concrete production, you could have some chlorides in there. It is wise to test to make sure that you do not have them in there, or if it's sufficiently low, that might be acceptable. Unfortunately, I do not know if sufficiently low is a valid response. I'm not sure of the value, if it is below a certain value, what the value would be. Chlorides can also come from external sources, and chlorides penetrate concrete through various transport systems. Again, the chlorides get into your concrete with water. So as soon as the water is able to be sucked into your concrete, it pulls the chlorides with it in there. So you all remember that the highly alkaline environment of your hydrated cement paste provides a passivation layer that protects your embedded reinforcement. Now, what free chloride ions does, they dissolve in the pore water and will destroy that passive film around the steel, causing a anodic ion dissolution or rust, as we know. Chloride-induced corrosion of reinforcement may cause accelerated corrosion if the chlorides are spread over the surface of steel. If you have a sufficient supply of oxygen, a rapid dissolution could occur, creating deeper pits, leading to considerable reduction in load-bearing capacities. Carbonation further encourages the neutralization of those hydration products until the passive layer becomes unstable. And that just becomes downhill from there in terms of rust. Interesting thing, this is a little picture of Friedel salts. Now, Friedel salts are formed when chloride ions move into your concrete matrix, and it reacts with C3A. Now, these Friedel salts will then also aid to make your concrete less permeable. So it then prevents the rate of chloride introduction or the chloride entry inside your concrete. So it reacts with the cement hydration products as they pass through the concrete matrix. A large portion of the chlorides will be bound by the cement paste, physically and chemically. So chemically by reacting, forming a Friedel salt, but then physically as well, if the Friedel salt crystal is formed now, traps a chloride ion. That ion cannot go and do any damage. It's now been secluded from everything else around it. And chloride binding is beneficial for durability as that reduced amount of chlorides in the pore water. Two types of chloride must be distinguished from. You have free chlorides in pore solution, and then you have chloride ions bound to hydration products. Only the free chlorides will have an impact on actual corrosion. So as soon as you have bound them, they become null and void. They become innocent bystanders. They cannot participate in the destruction. Only the free chlorides will have an impact on actual corrosion. Cement containing a relative high C3A content is desirable due to the chemical binding of the chloride ions to create Friedel salts. Concrete containing fly ash is known to bind chlorides by way of absorption due to surface forces while reacting to form more CSH. So while the fly ash is forming CSH paste that densifies up the matrix, these chloride ions that is in solution and also around gets chemically bound, physically bound, being absorbed by the process. So they get bound in the perimeter or the outside surface of your concrete. While carbonation might then further release some of the bound chlorides over time, local investigations of old structures in Cape Town have proven the benefits provided by fly ash concretes. So the transport mechanisms for chloride attacks, the mechanisms of penetration are by capillary absorption, hydrostatic pressure, and diffusion. Diffusion is mainly the mechanism that drives chlorides deepest. So typically your surfaces that will be at higher risks, surfaces where chloride concentrations are high, which stands above reason, and then surfaces exposed to wetting and drying cycles. The water goes in there, takes the chloride ions in, the tide moves out, and your structure literally evaporates. The water evaporates, but your chloride ions stay in the concrete. Then comes high tide again, and it's pulling more chloride ions into your structure and low tide. So as soon as the water ebbs and flows, you will have a higher risk. So the use of pozzolans in cement and concrete reduce the permeability, reducing penetration of chlorides. Chlorides are also chemically bound by pozzolans. So the luminous-siliceous materials such as silica, fume, fly ash, and GGBS. The pozzolanic reaction produces the additional calcium silicate hydrogel. Now, this you'd remember from last week. The fly ash is very beneficial in that. It reacts in that alkaline nature, and it produces more CSH, reducing permeability of the concrete. If you have a concrete with a lower water demand, that is very beneficial. It reduces the amount of capillary pores in your concrete. There are less routes of entry for the baddies to get inside your concrete.
Hi, Rian, it's Morris here again. It's not in particular the chloride attack. It seems to me that if you can get your concrete mix design to use less water, it's better for the concrete overall.
Absolutely, absolutely, yes. And not just for chloride attack per se. It is also beneficial for sulfate attack then. It's also beneficial for anything that could or would want to get into your concrete, and that could possibly even CO2, even carbonation. The denser your concrete matrix, the more durable the structure becomes. And if you reduce your water demand, if you steer away from too much paste, in other words, as soon as you have a pump mix, you have a higher paste content in your concrete, because your smaller aggregates, if you use 13 millimeter stone in your pump mix, there's a higher surface area And the best way to describe this, if you were to imagine a concrete with 19 millimeter stone, excuse me, and you were to take one of those 19 millimeter stones, and you were able to break it in half, what happens to the surface area of that two halves of a 19 millimeter? You end up with two extra surface areas to that aggregate. It's like breaking a muffin in half. You end up with more surface area. So if you have concrete, your cement and your hydration products has to coat everything in your concrete. It does coat everything. That solution of oil and cement particles covers everything. So the more surface area you have, the more paste you have. And you remember that shrinkage and creep is related to your paste. So it's a moisture dependent thing. And if you have a lot of moisture in your concrete, that moisture wants to get out at some point. So if it settles and bleeds and you didn't recompact your concrete, you end up with a lot of capillary pores that actually causes you to have porous concrete. Concrete becomes almost like a sponge, where it will want to suck water continuously, or anything else for that matter. If it can take water, it will take CO2 also. So yes, you are right. In general, if you can end up with a more denser concrete matrix by applying a fit for purpose application, you cannot use a low slump concrete if you have very congested reinforcement. It will not move through your reinforcement. So that stands to reason. You'll end up with honeycombing and you'll be in a bad space if you've specified a low slump concrete for the application where you have very restricted movement of your concrete in terms of placing the fresh concrete. So the concrete needs to be fit for purpose. That is the number one consideration, I would say. Your concrete needs to be the right guy for the job. It's like sending a replacement player onto the field. That guy that you send up needs to effectively replace the person that was in that position a few minutes ago. And you need to send the right guy in there. So your concrete, if it's dense enough, and your concrete has been well thought out for the application, yes, you will end up with less trouble. Yes, you might think maybe there's like a MacGyver mix. I can just specify this one mix for the rest of my life, and it will cover chlorides. It will be sulfate resistant. It'll be fine for heat of hydration. It'll be. You can list it. I say yes, but also no. You could rather have something that is more specific for the application. Look at the considerations. I see a question here from Ruben, and he wants to know if your structure is under chloride attack, how can you determine that? And Ruben, yes, eventually it will have an effect on your surface. But what happens if it's gone too far into your concrete, and too far, any distance in your concrete would be deemed too far, I dare say. It gets to your reinforcement, and your reinforcement starts rusting. And your anodic ion dissolution is a swelling effect. So your reinforcement literally starts spalling your concrete off your structure. And that is when chlorides are getting in there. That's typically what you'll see. Thanks, everyone. It's been a pleasure.